Hello children, we are going to see a new concept today. Concept is related to circular motion of a point mass. See, this relation we know, V is equal to omega cross R in case of circular motion of a point mass, right? Where V, what is this? It is the linear velocity, and this is angular velocity, and this is the position vector of the point mass on the circular path. Okay? This relation, how is it being established? What I want to say that when an object is or point mass is revolving along the circular path, then how this relation is being established. We will look at this. Suppose this is a circular path of the point mass. ऐसे assume कर लो, ठीक है? Center is here, and this, suppose these are the two positions of the object. These are the two positions. Suppose initial position is P1, it has come to P2, right? This is a circular path. It is plane is perpendicular to this board, right? And it is the perpendicular line to the plane, to the circular path, right? Now, if we consider this point as origin of the coordinate system, suppose this is the coordinate system, x-axis we assume, and this is, suppose we are assuming y-axis, and this is as z-axis. This is the coordinate system I have made. Okay? This is the coordinate system. Origin is this, and this point mass is making this circular path in this plane, in xy plane. This is the xy plane, right? And xy, this is the axis I have shown, and this is the perpendicular, this is the z axis, and this is revolving around this point, means about this axis we can say, right, for a point mass. And or we can say in the rigid body I have chosen one point which is in the circular motion, it is there when it is rotating about z axis. Every mass, every point of that rigid body is making the circular path. So one point I have chosen, and I have made the path of this. Now, in case of circle, we know one thing. Suppose this is the position vector of this point P1, which has moved and it has reached up to P2. That is the position vector is R. The origin from here is the position vector. After some time, it has moved up to P2, right? And this distance is very small, suppose the delta theta. And this linear path P1, P2 will be supposed to delta S. So we know one relation. Delta S is equal to this delta S along this circular path, and this plane is perpendicular to this. That is why I have shown elliptical. It is not exactly circle. So if I would have chosen this plane of the circular path, figure would have been different. Why did I make like this? To show you that this omega, angular velocity, will be along z-axis. That I wanted to tell you. Right, delta S is equal to R, the magnitude of this radius vector or position vector of P1, right? Magnitude is R, and this is delta theta, right? Suppose this distance from P1 to P2, it has taken a small time, that is delta t. So we will divide both the sides by delta t, then we will get this relation, delta S upon delta t is equal to R delta theta upon delta t. R I have taken as constant. Why? Radius of this circular path is not changing. But this angle at every point, different positions of this point P1 will go, and this theta will go on changing. That is why theta is variable, and accordingly this path along this circumference of the circle, this will also go on changing. So delta S is variable and delta theta, this is a change I have taken. So if this is theta, then this is delta theta. If delta t tends to 0, if delta t is very small, from P1 to P2 it has gone, I have taken considerable length, isn't it? And delta t I have considered. If delta t is very small, then we know limiting condition we will look at, limit delta t tends to 0, delta S upon delta t is equal to R, limit delta t tends to 0, delta theta upon delta t. This much we understood. Okay, this part, what is this? It is delta S upon delta t is equal to ds upon dt is equal to R d theta upon dt. So it is also dt. This is what? This is the linear velocity of the particle at this point, and linear velocity is always tangential to this circular path, right? And this d theta upon dt is the angular velocity, and angular velocity is always perpendicular to the plane in which the particle is revolving, right? So omega will be along, this will be along omega vector, angular velocity will be along this, and object is revolving like this anti-clockwise. Since it is anti-clockwise by right hand rule, so this is the direction of rotation in this plane, and this will show the direction of angular velocity. So omega will be along this, and particle is moving in this plane. In this plane, it is moving like this anti-clockwise. So using right hand thumb rule, motion is like this, so this is the direction of omega. So we can write this is V is equal to R omega by magnitude. If I have to show, you see, in the vector form, if I have to show, then it should be written that for V vector is equal to omega cross R. Why is it like this? See, omega, this is the direction of omega parallel to this. So this is omega, this is R vector, this is omega, omega cross R by right hand rule, omega cross R, then the direction of velocity will be perpendicular to this board and inside the board, and this is V. This is V vector. This V vector is, since plane is like this, velocity vector is like this, tangentially inside. This V is tangentially inside. This is omega, this is R, so omega cross R. Omega cross R means V will be inside, omega cross R. Omega cross R. This thumb tells the direction of V, and this can be shown over here. That is why V is equal to omega cross R we write. Right? So this relation could be put. And omega cross R means what? Magnitude of omega into magnitude of the radius vector into sine of the angle between omega and R. So see, what is the angle between omega and R? This is the vector R, this is omega vector, so angle between this is 90 degree. So with this we can write magnitude of V, suppose we have to find that is magnitude of omega into magnitude of r vector sine of theta. In this case, theta is 90 degree. Therefore, V is equal to omega r. We got the same thing over here. So, this relation we could see when the origin, center of the circular path is considered as origin of the circular, origin of the coordinate system, right? Now, if this origin is shifted somewhere along this z-axis, still we will get this relation that we have to show. Now see children, slight change I have made in this. Initially, in coordinate system, coordinate axis was the origin, that was the center of the circular path. Now, I have changed the position of the origin from where the position of the particle is being observed, right? The position vector is now this. Previously, position vector was from here, origin was at the center. Now, origin I have changed along the axis of rotation, right? Now, this is R. Suppose center of the circular path is over here, that is C, and radius of this circular path is capital R, right? A small angle it has moved, that is of delta theta. So, new position as I had shown over here, this P2, this is very small, very close to this. So, I will consider this another vector, and this is also same as this one, that is the vector R, since it is very small, because I am going to see that delta t is tending to 0, approaching to 0. It means this distance P1, P2 will be very small. Here also I can write delta S, that is along this circular path P1, P2, P1, P2, this is distance and this is delta S. Delta S is equal to capital R into delta theta. In geometry in the lower classes we have studied R into delta theta is equal to delta S. This is measured along the circular path. Now, and suppose it takes time delta t, right? So therefore delta S upon delta t, we will divide both the sides by delta t. Time taken by the particle P1 to reach at P2, right? So it will be divided by delta t, we will get R delta theta upon delta t. If this delta t is very, very small, very, very small, so new position P2 will be very close to P1, means position vector of P2 will be same as that of small r vector, right? And this r will remain same because the radius of the circular path capital R is not going to change. So we can write if delta t approaching to 0, therefore limit delta t tends to 0, delta S upon delta t is equal to R, limit delta t tends to 0, delta theta upon delta t. Since delta t is approaching to 0, this becomes ds upon dt is equal to R d theta upon dt. As we know, d theta upon dt is angular velocity, this is linear velocity, this is v, therefore v is equal to r omega. This can further be written as v is equal to, what is r? Suppose this is omega, direction of omega is this only, perpendicular to the plane. In this plane circular path is there, perpendicular. In this plane circular path is there, so perpendicular to this will be the direction of angular velocity. So we can plot over here parallel to this. I will draw, this is omega, this is r, so this angle I have chosen at, suppose this is theta, right? So this will also be theta, and these two are parallel alternate angle, this will also be theta. So this is 90 degree. So in this right angle triangle, capital R will be, this is magnitude of a small r vector sine theta. Here we will get R is equal to R sine theta, right? So here R vector mod, that is equal to R. This is the thing. So in place of R, we can write R sine theta over here. So we will get R, that is small r sine theta. Small r sine theta into omega. See, what is this? V is equal to R sine theta omega. We can write omega cross R vector. That is magnitude of omega, that is this, magnitude of R, that is this, and angle between omega and R is theta, and that is sine theta. So this is R vector, this is omega vector, and this is angle between these two vectors is theta. So R omega sine theta can be written as omega cross R. In the previous case also, in this case also, we had got V is equal to R omega cross R, we got over here also, right? In this case also we got omega cross R. What the difference does it make? Only thing I wanted to show over here is, even though along the axis of rotation the origin is shifted, this relation is not going to change at all. I have shifted from here to here, I have shifted the origin, coordinate axis I have changed, origin is shifted over here. Still the relation is intact, the relation is not going to change. So irrespective of the origin chosen along the axis of rotation, this relation will hold, where R is the position vector of the position of the particle which is in circular motion. This is very important relation that you must know. This is the proof of it. So children, the next bit, very important concept I will tell. Till then, all the best. Take care.